and, m tilde of I is the ith entry of memory, like the value stored at the ith memory cell. Okay, and because we have a read-only memory here, this is all fixed. Like, M does not change over time. There's no writes to memory happening in this review of Shout. With Twist, there will be writes to memory happening. Okay, so that's the setup, and the prover wants to prove that for every Boolean input to RV. So let's say okay. So if let's say there are capital T reads to memory, then RA twiddle and RV twiddle. Well, let's just say RV twiddle. RA twiddle is a bit of a is a little bit different, but RV twiddle is a log T variate multilinear polynomial. Okay, and so the claim is that for every input j in 0, 1 to the log T, RV twiddle of j is what it should be. That is m twiddle of, I'm going to abuse some notation here. I'll just say m twiddle of the address read at cycle j, like the address read, at time j, according to RA. Okay, and yeah, so that claim is basically saying that RA is telling you the addresses that are read by each read operation. So just an ordered list of RA is giving you an ordered list of addresses. At time 1, I read this memory cell. At time 2, I read this memory cell. At time 3, I read this memory cell. And RV is supposed to be the values returned by those read operations. So the prover's claim is that, for every read, for each one of the J reads, RV twiddle evaluated at J is exactly, M twiddle, that is the memory, the value residing in memory at the jth address. Okay, and in Shout, the addresses are in one hot form. They're in, let's say 0, 1 to the memory size, capital K, where, the ith memory cell corresponds to the ith unit vector, so all zeros except for 1, 1, and this 1 is at, location I. So in this situation, RA is actually a log memory size plus log number of reads, which is T, variate multilinear polynomial. And if you feed it, the binary representation of an address and the binary representation of a cycle, it spits out 1, if address K is read at cycle J, and 0 otherwise. Okay, so that's why I wrote this funny thing here. The address read at cycle J according to RA, is it doesn't make sense to say RA of J, right? Because this one hot encoding thing means RA actually takes kind of, 2 different inputs conceptually, both a memory cell, a memory address, and a cycle. And so, by the address read at cycle J according to RA, I mean the unique K, in 0, 1 to the log memory size, such that this equals 1. That's what one hot encodings do, is, they every read gives you actually, K different values, but they're all 0 except for the one cell that's actually read at that step. Okay, so that was the setup, and the claim is just, hey, all of these committed values are indeed the values stored at the appropriate memory cell according to, the committed addresses. Okay, and so the core of Shout is really at its core just a single instance of the sum check protocol. And so let me write what it is. So it's just a special expression. Make sure I don't mess this up. I'm actually going to just pull up the paper real fast. If I can, 80% chance I do it from memory with no errors, but better to get 100% chance. Here, okay. Oh, that didn't work. I pulled up the wrong thing. All right, I'll do it from memory. So here's the fact. So RV twiddle evaluated at R, and now this is like the true read values, the true values returned by all the reads. Maybe I'll stick a C in front of it so that this is the the RRV, so the real read values. So that if I take the multilinear extension of the correct values returned by all the reads and evaluate it at a random point R, this turns out to be the sum over. Am I going to mess this up? Perhaps I would. So okay, let me see if I can get this right. So we have EQ twiddle of so we have a sum over cycles J, so J and 0, 1 to the log T, of EQ twiddle of R comma J, okay, times R A twiddle of R. No, R is a cycle. So where is this address coming? So I guess there's a sum over yeah, this is why I wanted the paper up and I didn't get it. So it's a sum over J and 0, 1 to the log T and K and 0, 1 to the log K, log capital K. Okay, so RA twiddle of K comma J times M twiddle of J. Okay, that's it. That's it. That's the whole thing. And yeah, actually, we can just prove this, really quickly. So to prove that this equality holds, you just confirm that the right-hand side is multilinear in R, and then you confirm that if R is a Boolean input, the right-hand side spits out the same thing as the left-hand side. You check those two things, and then the right-hand side and left-hand side must be the same polynomial, because a multilinear polynomial is uniquely determined by its evaluations over Boolean inputs. The Boolean hypercube is an interpolating set for multilinear polynomials. So it's easy to check. R only appears in the right-hand side here, being fed into EQ twiddle. This is the multilinear extension of the equality function. It's come up every time we've seen the sum check protocol, essentially. Yeah, so R only appears here, getting fed into a multilinear thing. So the whole right-hand side is multilinear. Okay, and then if R is in 0, 1 to the log T, we want to confirm that the right-hand side and left-hand side spit out the same thing. And what's going on is we have this big sum over J, but every J just gets killed by this EQ twiddle term unless J equals R. And in the event J equals R, what we have is, a sum over all addresses of RAKJ times MJ. And this RAKJ is spitting out 1, like only if K is the actual memory cell read at cycle J and 0 otherwise. So, the EQ twiddle, kills all J's not equal to R. It kills, all but 1 cycle. And the RA twiddle kills all but 1 memory cell. And what comes out, from the one term that doesn't get killed is M twiddle of J, with, and J equals R. So that's exactly what you, sorry, I'm M twiddle of K. Sorry about that. So that's exactly what you want. So every term is killed except for the K, that the memory cell K that is actually read at cycle R, and that term that's not killed spits out M total K, which is exactly what you want. So if R is in 0, 1 to the log T, the right hand side, spits out, M twiddle of K, where K is the address read at cycle R, which is exactly what we want. Okay, so this is shout right here is in any kind of ZKVM, the prover the verifier ultimately just needs to evaluate the values returned by all the read operations at a random point, and this is how that one evaluation gets proven to the verifier, right? So last time I mentioned, these values don't ever even need to be committed. It's cleaner to define the problem as if they're committed, but it turns out with shout they don't have to be. The snark verifier ultimately just needs to evaluate the multilinear extension of the correct read values at a random point. So when the verifier, says, hey, I need to compute, this one evaluation of that polynomial wasn't committed. So please, prover, help me get that evaluation. I have no way to do it on my own. They just apply the sum check protocol to compute this big sum. And at the end of the sum check protocol, the verifier just has to evaluate, EQ twiddle at a random point, RA twiddle at a random point, and M twiddle at a random point. And, EQ twiddle, the verifier can get that evaluation on its own in logarithmic time. M twiddle, it sort of depends if the lookup table is structured, which is the case for all the tables arising in Jolt. The verifier can get M twiddle at a random point on its own in logarithmic time. If M twiddle is not structured, an honest party would have committed it in pre-processing, and then the prover would be providing the random evaluation of M twiddle. And then RA twiddle is committed by the prover, and the verifier gets the necessary evaluation from the commitment scheme. Okay, so that's shout. Kind of a very detailed in the weeds, recap, but took about, I guess, 10, 15 minutes. Hopefully it was worthwhile. Let me pause here, see if anyone wants to ask any questions before we dive into Twist. Bobby, did you figure out your volume?
Hey.
Hey.
Yeah, I'm still confused about why the distinction between the values, the WR. What's the deal there? I don't get it.
Say that one more time. Your audio was just a little. What's the deal with what values? Oh, why does the verifier only ever have to evaluate the read values multilinear extension at a random point? Is that the question?
Sorry, can you hear me better now?
Yeah. So now I can hear you more clearly.
Okay, great. Sorry. No, I'm just wondering the difference between the RB and the double RB.
Yeah. Okay. All right. Good.
Maybe if you mean with like real return value.
Yeah. Okay. Yeah. Thanks for asking. I can see why that would be confusing. Okay. So the deal is, this is the reason there's two different things here is just coming from the disconnect between how I define the memory checking problem in the first place and how the protocol actually winds up working. So I define the problem with the prover committing to a vector, a multilinear polynomial, claim to be the correct read values, but it might not be. The prover could be lying. Okay, and so that's how I define the problem. But maybe I shouldn't have defined it that way, because in the end, that commitment to claimed read values is just not actually needed. Okay. I think the problem just feels cleanest to define if the prover, commits to the claim read values and the addresses, and then proves that the claim read values are actually equal to the real read values. Okay, but in practice, it turns out the prover never even needs to commit to the claim read values. Why? Because like in a broader snark that invokes the lookup argument, the snark verifier will only ever need to evaluate the real read values at a random point. Okay, which means the prover never even needs to commit to, you know, any claimed read values. Right. So that's what's going on. Is like I define the problem with the prover committing to something that's claimed to be the correct read values, but might not be. But here I really meant the correct read values. And then so in practice, the way we're like going to put shout into Jolt, what's going to happen is there will not be a committed claim vector read values. Instead, the Jolt verifier is kind of just going to pretend like the read values were committed, but they're not. At some point, it's going to have to evaluate the multilinear extension of the correct read values at a random point, and when that happens, it's going to say, "Hey, prover, help me out here because I have no way to get that evaluation on my own." And the prover is going to say, "Okay, let's apply sum check to compute this big sum," and at the end of the sum check protocol, we're going to be okay, right? Because you're just going to have to evaluate EQ twiddle, M twiddle, and RA twiddle at a random point, and now you're good. Now we have ways for you to get each of those evaluations. Did that clear things up? I apologize that I did things in this confusing way.
Okay, so it's just RV would be like a claim, and this is like the actual thing.
Yeah, it's like, yeah. So the way I defined it, like RV twiddle is claimed read values, and RV twiddle is the real read values. But like the way this will actually get applied is there will just be no claimed read values at all. So the way I think one should conceptualize what's going on here in the end is that RRV here is a virtual polynomial. So just forget that I ever said that the prover is committing to claimed read values. Just forget I said that. So RRV is a virtual polynomial. What that means is the prover's not going to commit to RRV. The verifier is going to nonetheless pretend like it was committed. If RRV like had been committed, then then I would be getting rid of the R there. Anyway, if it had been committed, the verifier could just get the evaluation from the commitment, but then it would have to separately check that the committed thing equals the real thing. Here, what's going to happen is when the verifier needs to evaluate, the virtual polynomial at a random point, it's going to use sum check to get the evaluation. And at the end of sum check, the verifier is only going to have to evaluate things that either were committed or are quickly evaluable directly.
Okay, but I just think this like
okay. Yeah, no, it's my fault. It's my presentation here is just not clear. So I guess we can. Yeah, thanks for the question. We can try to revisit later. Yeah. Okay. Other questions?
I wonder if it would be feasible to add zero knowledge to it, or is it done outside the lookup argument somehow?
Yeah, it should be doable to just kind of directly add zero knowledge. This is basically always the case. Like it's painful but doable. There are known. You kind of need two different components to make it zero knowledge. One is you need a zero knowledge analog of the sum check protocol that kind of masks each prover message and it kind of blinds each prover message in each round. And there are known ways to do that. And then on top of that, you need a hiding or blinded version of the polynomial commitment scheme for RA twiddle. And there are known ways to do that as well. If you actually work through all the details, it gets pretty nasty. So I'll just leave it at that. And then, if you don't want to work through those details and suffer through the nastiness, you can always, like take your non-ZK proof and then ZK prove, the non-ZK proof.
Mm-hmm. Yeah, that's a great perspective. Uh, does it imply that uh, does it imply that while making shout zero knowledge, uh, RRV must become it becomes a must to the polynomial being committed, and it's not virtual anymore?
That is an excellent question. I think you should be able to get away with committing only to a blinding factor, which is like much smaller than, RV twiddle itself, or, I really botched everything with the RRV and RV. Yeah. So you should only have to commit to a small blinding factor is the short version. Again, the details are nasty. Actually, a lot of papers that have studied exactly this have messed up some details. And it's actually a significant gap in sort of the literature and in practice, because there are projects that are interested in using shout in ZK contexts, and actually this is a big hangup, that these details that have there have been like a series of papers that have each kind of missed some little things, and I guess either the implementations weren't ZK, or they were, just attempted ZK, but like, not actually ZK because they missed some. So anyway, yeah, so that's it. But that's it. And, in principle, you should just have to commit to a blinding factor. That shouldn't be a prover bottleneck. But the details, actually could use a yet another paper, I think.
That's very interesting and great perspective again. Thank you.
Yeah, thanks for the question. Okay, yeah. So, despite the horrible confusion I created between RV twiddle and RRV twiddle, I think you can just think of shout as just a really nice expression for the correct read values multilinear extension at a random point. That's it. So it's kind of just a way to make the correct read values multilinear, needs to evaluate that thing at a random point. It's able to get that evaluation despite the fact that it wasn't committed. Okay. So hopefully fusion. Now let's go to twist. Okay, so each cycle is, I think the paper does a read followed by a write, but I actually think I'm going to wind up switching that in the paper as well as today to a write and then a read. Okay, and it doesn't. It is things deep in the weeds of twists. I think life gets easier if it's write then read rather than read then write. But don't worry about it. So yeah. So what we're going to have is a committed polynomial of write addresses and a committed polynomial of write values. Okay. Then a committed polynomial of read addresses and a committed polynomial of read values. And again, these two things are, log k plus log t variate polynomials, multilinear polynomials. And these two things are log t variate multilinear polynomials. Okay, and the provers, well, again, I actually, let me try to improve my presentation this time. Let's say RV twiddle will not be committed, in fact. So let's say RV twiddle is going to be a virtual polynomial. Okay, and so let's just define it directly to be like the correct read values. Okay, so we're just going to define now. I'm trying to avoid the confusion I created before for shout. let's just define RV twiddle at any cycle j to be the value stored at memory cell, specified by RA twiddle of j, blah, comma j. So that, this means by the memory cell specified by, in other words, this is the unique little k in 0, 1 to the log, memory size big K, such that RA twiddle of k comma j is 1. Okay. So now, now that I'm doing things in a hopefully less confusing way, RV twiddle is just defined to be the correct read values, the correct value returned by every read. Okay. And so, and so by the value stored at memory, a given memory cell at cycle j, what do I mean by that? So let me change colors here. So the value stored at memory, at a given memory cell, at cycle j. Okay, what I mean by this is, I mean WV of j prime, where j prime is, the, cycle, less than is the largest cycle less than j, for which W a twiddle, of blah comma j equals, W, R a twiddle of j prime. Yeah, okay, sorry. So let me say this another way, since that didn't come out in a very easily understandable thing. This is just the value written to cell K, where K is the cell read at cycle J, most recently, as of cycle J. Okay, so with apologies for the stumbling, what it means for the prover to be maintaining memory correctly is that the value returned by every read operation is indeed equal to the value most recently written to that cell, the cell that was read, at the time the read occurred. Okay, so it's like if you're doing a read during the 100th cycle, right, that read should return the value currently stored in, that memory cell at the 100th cycle. What is the value currently stored in that memory cell? It is the value that was most recently written to that cell. Okay, that's what I'm trying to say. So W a twiddle and W v twiddle specify the writes, what value is written to what cell at each time step. R a twiddle specifies, the reads, and RV twiddle is like the actual values returned by those reads. Okay, and so what Twist is it like a protocol? The shout was a way to get the verifier RV twiddle evaluated at a random point R. Twist is the same way. So Twist is a protocol, to compute RV twiddle of R, for any desired evaluation point R. Okay. Questions about that setup or definition? Hopefully that was a little clearer than the shout setup, even though I stumbled pretty badly over, defining what the correct value returned by each read is. Okay, no questions? All right. So if there are no questions, I'll start giving the Abhi, do you want to just confirm I'm still audible?
Yeah, everything is okay.
Okay, great. Great. Okay. So yeah, let's start talking about how the protocol works. So we're going to have another. So remember, this whole thing about computing RV twiddle of R, even though RV twiddle is not committed, that's making RV twiddle a virtual polynomial. Okay, we're going to have another virtual polynomial in this protocol as well. Okay, that polynomial I'm going to call M twiddle. Okay, but in Shout, M twiddle was like fixed in advance and log t variate. Okay, here M twiddle will be log memory size plus log number cycles variables. And if you feed it a memory cell and a time step, this will spit out the value, the real, the actual value, stored at cell K at time J, meaning at the time of the Jth read operation. Okay. Yeah. So we're going to ensure that the prover doesn't have to commit to mtwiddle, but we kind of want to use mtwiddle inside the protocol, inside various sum checks. So we're going to wind up doing two things. We're going to kind of use mtwiddle to give the twist protocol. And separately, we're going to have to give a way for the verifier to evaluate mtwiddle at a random point, because it's virtual, it's not committed. Okay, but before we do either of those things, let me discuss why it's so important, why we need mtwiddle to be virtual for performance reasons. I say with RV twiddle, twist and shout allow it to be virtual. That is important in some applications. In the performance of some applications. We discussed this briefly last time, I think. This what do we call it? Speedy Spartan stuff. It's like super important. That's a snark for general constraint systems. It's super important that RV twiddle is virtual. But like in Jolt, in a ZKVM, it's not a big deal, right? Like maybe we're going to get a 10% prover speed up by not having to commit to something claimed to be RV twiddle. But with this mtwiddle thing in Twist, this we fundamentally need mtwiddle to be virtual, or the performance will be awful. Okay, why? It's because mtwiddle is log k plus log t variables. Okay, so that means mtwiddle is a size capital K, meaning memory size, times capital T polynomial. An interpolating set for mtwiddle has size capital K times capital T. It's kind of telling you for each and every one of the capital K memory cells, what is its value at each and every cycle. Okay, and so we cannot afford, the prover cannot afford to commit to that many values. Like we can't even afford like K times T field operations unless K is tiny. And committing to a value is like minimum of 6 field operations or something. So we simply cannot afford to commit to KT values, and so it's that's why we fundamentally need mtwiddle to be virtual. We just can't commit to it. Okay, so what is the prover going to commit to instead? So what P will commit to is what I call increments, inktwiddle. Now, inktwiddle will also be a capital K times capital T size polynomial. Okay, so this is the same number of variables as mtwiddle. Okay, so this is also log memory size plus log, num cycles variate. Okay, so that's a little weird, right? I just said we can't afford to commit to that many values, and this thing also has like the same number of of values. The key though is that ink twiddle will be extremely sparse. Okay, so ink twiddle of kj will be non-zero for only one value of k in 0, 1 to the log capital K for each cycle j in 0, 1 to the log capital T. And so this means that we even though it's the same number of variables as mtwiddle, it's vastly faster to commit to. So we can, or the prover can, commit to ink twiddle with about T group operations. If you're using an elliptic curve commitment scheme, it's like you only pay for the non-zeros, right? So this was the same reason we use one-hot encodings. It's like you can have very, very big vectors. If they're very sparse, they're almost all zeros. You only pay for the non-zeros. Ink twiddle is exactly leaning into that same property. Ink twiddle is sparse. Okay, so what is ink twiddle? If I evaluate ink twiddle at a memory cell and a time step, this will just be m twiddle of I guess k j minus 1 minus of j minus m twiddle of k comma j minus 1. Now this notation is terrible here because here j is really in a binary vector, and so by j minus 1 what I really mean is the binary representation of like the integer represented by j. So int j, I mean sum over the bits of j of like 2 to the I times j sub I. This is the integer represented by j. Minus 1. Yeah, so this is I'm calling this ink for increments because it's the amount by which memory cell k got incremented at by the jth write operation. Yeah, it's the difference between the value stored in memory cell k at time j, compared to the value that was stored at that memory cell at the previous step. Okay, and so because each memory only one memory cell is written at each step, that means only one register k, has a non-zero increment at each step. So that's what ensures that ink will be non-zero for only one memory cell at each time step, and that's what ensures that ink is fast to commit to. Okay, so let's come back to m twiddle being a virtual polynomial. So at some point in Twist, the verifier is going to have to evaluate m twiddle at a random point. Let me call it r comma r prime. R is log k, random field elements, and r prime is log t. So r prime is in field to the log capital T, and r is in field to the log capital K. That's a superscript. Yeah. And so I'm going to give a nice expression for m twiddle as a big sum of evaluations of involving ink twiddle. Okay, so here's a fact. So m twiddle of r comma r prime equals, hopefully I don't mess this up, the sum over all cycles j of so j in 0, 1 to the log t of ink twiddle R is, so think of R as the address, the register. I use these terms interchangeably. I'll say like, address, memory cell, register, all interchangeably. And R prime is like the cycle. So we want to focus on register R, but we want to look at all the let's say all the increments. Okay, but really we only want to look at the increments that are strictly less than cycle R prime, right? Like n twiddle is the value stored at register R at time R prime. So that involves just summing up all the increments for register R before time R prime. So now we multiply each increment by let me move everything over. Nope, not that. Sorry, bear with me one sec. Is this it? There we go. Move everything over. Good. Okay. So we only want the increments that are from time steps, before time R prime. So multiply by the function less than or equal to twiddle R prime comma J. Okay. So what is this? This is the multilinear extension of the function that takes as input two vectors, let's say J and J prime in 0, 1 to the log T, and outputs, 1 if, hope I don't get this backwards, if J, is the binary representation of an integer less than or equal to the integer represented by J prime, and 0 otherwise. Okay, so that's it. So what this is doing is it's saying, hey, the value stored at register R at cycle R prime is a sum over all increments of the increments for register R at that time step. But kill any time step that is not less than or equal to time step R prime, because those are referring to future write operations that happen after time R prime. That's what's going on here. And so, you can easily check that the right-hand side, this big, this thing in the sum, it's multilinear in both R and R prime, right? Because R is fed into a multilinear thing inc twiddle, and R prime is fed into a multilinear thing LTE twiddle. And there's no, that's it. The R and R prime don't otherwise appear on the right-hand side. And the explanation I just gave tells you that, if R and R prime are in the hypercube, the right-hand side spits out the same thing as the left-hand side. Okay, so which means when the verifier wants to evaluate M twiddle at R comma R prime, we just apply the sum check protocol to compute this big sum. At the end of the sum check protocol, the verifier has to evaluate inc twiddle at a random point and LTE twiddle at a random point. Inc twiddle was committed, so you can get any desired evaluation of inc twiddle from the commitment because it was committed. And LTE twiddle is actually evaluable in log time, so it's like log T time evaluable. It's sort of like, it looks a lot like EQ twiddle. EQ twiddle arose in the shout PIOP, in the shout sum check. LTE twiddle is only a little bit more complicated than EQ twiddle. So that's how we make this M twiddle, that tells you the value of every register at every time step, a virtual polynomial. We commit to inc twiddle, which is sparse and hence fast to commit to, and then give this nice expression for M twiddle evaluations that lets us kind of, from the verifier's perspective, reduce evaluating M twiddle at a random point to evaluating inc twiddle at a random point. Okay, so that's how we make M twiddle virtual. Questions?
How does verifier knows this value to actually sum check to do sum check with prover? I feel a little bit lost the logic here.
Yeah, so no, it's an important question. So thanks for asking it. So, the sum check protocol is a funny protocol where, we always say apply sum check protocol to, polynomial G, to compute the sum of all evaluations of G in the hypercube. And, that language suggests that both the prover and verifier know exactly what G is. But in fact, the verifier ultimately just has to evaluate G at a random point. And so it doesn't, need to know everything about G. The prover and verifier can apply some check to G as long as the verifier can evaluate G at a random point. So here what's going on is, in Twist, I haven't covered all of Twist yet, but at some point in Twist, the verifier will have to evaluate M twiddle at a random point. The verifier will know that random point, R comma R prime. So the verifier knows R comma R prime. And, the verifier is then going to say to the prover, hey, prover, tell me, M twiddle of R comma R prime. And the prover is going to say, okay, now we're going to apply the sum check protocol to G, where G is, so G of X here, this is log T variant. The G of X in this sum check is defined to be inc twiddle of R comma X times LTE twiddle of R prime comma X. Okay. And so, yeah, and so inc twiddle was committed. And so what I'm saying is the verifier, does it know inc twiddle? Well, not really, but it has a commitment to inc twiddle. The prover sent it to commitment. So it doesn't matter that, it only has the commitment to inc twiddle and otherwise has no idea what inc twiddle is. They're just going to apply the sum check protocol to this G. At the end of the sum check protocol, the verifier has to evaluate G at a random point. And, the verifier can do that because it can get the evaluation of inc twiddle from the commitment to it, and it can evaluate LTE twiddle on its own in logarithmic time. Did that clear things up, or is it still confusing?
Yeah, it cleared it up. Thank you.
Okay, super important question. So again, thanks for asking it. And if there's something else I can say to clarify things further, let me know.
Just very unusual to think about increment at the random point, since it has nothing to do with the increment itself, but multilinear extension. And it's little exploding in the head.
Yeah. I agree. It just takes some getting used to the sum check stuff. Everything, makes a lot of sense when inputs are Boolean, when R is R and R prime are Boolean vectors. Then you can literally think of R as a register and R prime as a cycle. But sum check requires moving off the hypercube into the whole field. And now these are not really, like a register and a cycle. So it just makes it harder to think about. But yeah, I don't know. It's like each value is indeed clearly like a sum of increments. That's what this is saying here. But ultimately, when you apply sum check, yeah, you've moved off the hypercube already. And that's just the way things go with sum check.
Yeah, thank you.
Yeah. Other questions?
So should we think as this as a trace for the register R up to that cycle?
Yeah, no, I think M twiddle you should think of as a trace, and in fact, it's kind of a trace for all of memory at every cycle, right? For every memory cell in every cycle, it tells you the value currently stored in that cell according to the right operations up to that point in time. So M twiddle is definitely a trace of just what happened in memory. Inc twiddle is also conceptually a trace of what happened in memory, but kind of zeroing out all the no-ops. So if a cell was just not touched at a given cycle by writes, inc will just have a 0 there. So yes, you can think of both M twiddle and inc twiddle as traces. It's just M twiddle, is kind of a dense trace. It has a non-zero value potentially for kind of every cell at every cycle, and inc twiddle is a sparse trace. It has a non-zero value for only one cell at each cycle. Does that answer the question?
Yeah, perfect. I did have a question from before. When you define start the protocol, you define that J was find something like the shade read. Maybe we can go up a little bit.
Sorry, the audio quality was just a little low. So I heard J and reads, but I didn't get the rest of the question.
Oh, sorry. No, if you can go up a little bit, maybe we can see
okay.
it there. It's in the start.
In here?
Or no, a little bit more.
For more up? Okay, say when.
I think we went too far.
We went too far. Okay, sorry, too fast.
Yeah, I mean, it was something about like J being only for reads, but I thought that J was like for cycles, and that would include writes and reads.
Yeah. Okay. So this language is confusing. I haven't figured out a good way for the language. So there are T cycles, but at each cycle, a write happens and then a read happens. Okay. So now M twiddle is determined only fully by the writes. Right. The value stored at each cell at each time step, that depends only on the writes. Right. So kind of as I just described, how M twiddle is a virtual polynomial, right? When the verifier goes to evaluate M twiddle at a random point, it can apply sum check to this increment, expression involving increments. All of that discussion only involved the writes, but like, we're going to have these variables like J, which I call cycle variables. And they're going to index. We're going to talk about the jth write, and we're going to talk about the jth read, and it makes sense because there are the same number of reads and writes. Like at each cycle J, there's a write that happens and a read that happens. Did that clarify things?
Yeah, I just missed the fact that at each cycle we have a write and a read.
Yeah.
It's fine now.
Okay, good. Thanks for asking. Yeah, that's important. Yeah, and it's annoying also, there's actually two T memory operations happening, but because I'm just assuming that they happen in this very structured form, write, read, write, read, write, read T times, and that lets me call say there are T cycles, each cycle is both a write and a read. Okay, so that makes M twiddle a virtual. Oh, another question. Go ahead.
Another small one. Yes. If the writing operation doesn't change anything, would it have a zero increment?
Oh yeah. I think there's nothing that stops. Yeah, it would just be a zero increment. That's right. So if you write a value, if you write a value to a cell at a given time step, and that value was already stored in the cell, it's just all capital K increments for that cycle would be zero, rather than one of them being non-zero. All of them would be zero. Yeah.
And it doesn't break anything in this encoding, in this Manhattan encoder?
Doesn't break anything. You'll see. So there's separately, we're going to have to make sure that this inc polynomial actually, is correct. so inc is. This is bringing up again, like, do I talk about, a claimed inc and a correct inc, or does that just confuse people? So this inc is committed by the prover, so it's like a claimed inc. So separately, I haven't described the whole protocol yet. Separately, we're going to have to make sure, we're going to have to check that inc actually corresponds to the write operation. So that inc kj is indeed, the increment that for cell k at time j based on WA twiddle and WV twiddle. So it's like WA twiddle and WV twiddle, those are the ground truths. Okay, that's by definition, like the correct, write values and write addresses. Inc is something the prover is committing to kind of help the proof system along. And so we can't just, trust that committed thing is the correct thing. We separately have to check it. Okay. Does that make sense?
Yes. Yes, it does.
Great. And so that's actually the next thing I'm going to cover.
Yeah, I mean, in my head, I guess it entails that ink, the return value of ink isn't Boolean, but it is, like, it is like, what would it be in a real system? A 32-bit value or a field element.
Yeah, exactly.
And
So
then,
it's field elements, but in like a RISC-V ZKVM, because every memory cell stores 32-bit values, the field elements that the honest ink would return are always in 0, 1 up to 2 to the 32 minus 1. So it's like, as far as the proof machinery is concerned, ink can contain arbitrary field elements, but in actual applications, the field elements that it actually kind of returns or evaluates to might live in some much smaller subset of the field. But this is actually important. Remember, small field elements are always, with the right commitment schemes and working over the correct fields and all that, faster to commit to than big ones. So the fact that, like in a RISC-V context, all of InkTwiddle's non-zero evaluations are in the small set. That's really nice, right? Because before I just said, hey, even though InkTwiddle has kind of KT evaluation, capital K times capital T evaluations over the hypercube, only T of them are non-zero. More is true. So all T, or at most T, non-zero evaluations of InkTwiddle live in this set, or maybe it's this. Maybe it's all you also might be as small as like minus 2 to the 32 plus 1. Just because increments are differences of two 32-bit values, and so that could be as big as 2 to the 32 minus 1, or as small as the negative of that. But either way, so these 32-bit values are much faster to commit to than arbitrary field elements. Did that make sense?
it makes sense, and yes, thank you. And this 32-bit values are only for Boolean hypercube. Outside of it, it's just random 256-bit field elements. Is it correct?
Yes, yeah. If you're using an elliptic curve commitment scheme, which forces you to work over a 256-bit field, that's correct. But just one clarification, just in case it's needed, maybe it's not. In terms of how long it takes the prover to commit to the values, all that matters is the evaluations over the hypercube, because that's really what the prover is committing to, is like just the vector of evaluations of the multilinear thing over the hypercube. But like then within the SumCheck protocol, like yes, like as soon as you move off the hypercube, this stuff is spitting out like arbitrary field elements. Yeah.
Yep, I was wondering if that would make sense to research for somebody to pack these values into the bigger one when you do the actual I don't know, commitment and so on.
Yeah, well, I mean, if you use Binius, Binius or Blaze or one of these binary field things, that's exactly what they would do internally to make the values really fast to commit to. Is they would pack several of these values into a single 128-bit field element or whatever. And then there's a lot to explore still within the SumCheck protocol about to what extent the smallness of like InkTwiddle over the hypercube can be leveraged. It's a challenge because, again, like as soon as you start bringing in random things instead of hypercube things, InkTwiddle starts spitting out random so that's why it's still a research direction to try to avoid that issue. So there have been some works that have, kind of found ways to keep more of the sum check provers work, kind of over the hypercube. So you don't immediately, move into, random field elements arising. But it's actually not clear that any of those techniques make much of a difference to something like Jolt yet. So still to be explored.
Thank you for this perspective. Thanks a lot.
Yeah, thanks for the questions. Okay, so coming back to the protocol, I'd say so there are two more things to check, right? Okay, so at this point, what we've done is we've said, the prover commits to the increments inc_twiddle, and m_twiddle is a virtual polynomial. m_twiddle stores like the value of every cell at every time step. Okay, because we gave away to evaluate, to kind of reduce m_twiddle, evaluating m_twiddle at a point to evaluating inc_twiddle at a point, and inc was committed, so that's fine. So there are two things actually left to check. Okay, so one is I guess the prover's original claim, which is, how to let RV_twiddle be virtual. That is, give like a nice sum check that expresses any of that, right, that means write RV_twiddle of R for any desired R, as a nice sum, involving only polynomials that were committed. So involving m_twiddle. And m_twiddle is not committed again, but like we've already dealt with making it a virtual polynomial. So that means that like from the verifier can kind of at this point pretend that m_twiddle was committed, because it's all okay. It's going to be able to evaluate it at a random point anyway, via the sum check we just discussed. And that's always the whole point of committing to polynomials, is to let the verifier evaluate them at a random point. And so then there's the question of make sure inc is correct. Okay, and so in Twist we call this the read checking sum check. Okay, because this sort of assumes that inc is correct, or that m_twiddle is correct. It's sort of a sequence of security, a way of, it's like. The sum check we've already seen for m_twiddle of R, R prime, that's going to give the verifier correct evaluation access to m_twiddle, assuming inc_twiddle is correct. Okay, the rechecking sum check is going to give the verifier query access to RV_twiddle, assuming m_twiddle is correct. But the assumption that m_twiddle is correct still depends on inc_twiddle being correct. And so the final thing, make sure inc_twiddle is correct. Okay. So so we call this the right checking sum check. So does inc_twiddle, which was committed, actually, have the right increments given, WA_twiddle and WV_twiddle, the rights. Okay. So let me start with the right checking sum check. So this is going to look a lot like shout. As will the rechecking sum check. I mean, shout is a rechecking sum check for read-only memory. So the rechecking sum check in Twist looks a lot like shout, and the right checking sum check also looks a lot like shout. So okay, so yeah, let's express the correctness of inc as a constraint system. I guess that's going to be easiest. So the real inc. Again, this nuisance comes up. The prover committed to something, claimed to be the correct increments, but now I want to talk about the actual correct increments. So the actual correct increments, k, j. What should that satisfy? That should equal right address twiddle of k, j times I guess it should be. I still haven't pulled up the paper on my laptop. I guess it should be. I'm gonna let me pull it up. I feel like there's a pretty high chance I mess it up if I don't pull it up. So just bear with me. Sorry. Go. Find the code box.
Is it okay to ask while you're searching for the paper?
Yeah, go ahead.
I wonder if to the checks that you listed, we should also check that ink is actually a hotshot, hot one,
Yeah. Okay. So
one shot.
no. So the right checking some check is about to guarantee that implicitly, right? Because the correct increments, we define increments, so that the correct increments have this property that this sparsity property, right? But because only one address is written at each cycle, there can only be one non-zero increment at each, for each cycle. And we're about to make sure that the committed, polynomial inc twiddle equals the true, increments. That's what the right checking sum check does. So a side effect of the right checking sum check is that inc twiddle better have that sparsity property. Does that make sense?
That sounds beautiful and intriguing.
Okay, great. Yeah. I mean, another way of saying it is like if the increments are correct, at that point I don't really care about the sparsity. Now the correctness of the increments, implies sparsity, so that's fine. But as long as the increments are correct, I don't intrinsically care about the sparsity, but for the fact that it ensures the honest prover is fast. And because the honest prover is honest, it's not really a security thing where sparsity is getting leveraged. It's a performance thing. So we're about to, the right checking sum check is going to guarantee that inc total is sparse, but security doesn't need that. All it really needs is that inc total is correct, but the correct thing is sparse, so you kind of get it anyway.
Mm-hmm. Sure.
Yeah. Okay. More questions? All right, so now I pulled it up. It turns out it's pretty embarrassing. I couldn't figure it out because it's very simple. So it's WV twiddle of that cycle minus M twiddle of K comma that cycle. Okay. Now this starts to get you worry about circularity in security here. I'll explain why this constraint system makes sense in a second. But I said, we gave a sum check that related an evaluation of M twiddle to inc twiddle. So sort of, the security of, getting the right evaluation of M twiddle depended on inc twiddle being correct. R comma J times LTE twiddle of R prime comma J. Yeah. So, if inc twiddle is wrong, then this is giving you the wrong the wrong evaluation for M twiddle. And now I'm checking that inc twiddle is correct, and my expression or my constraints for inc twiddle involve M twiddle, and so that feels like some circular security issue. And the correctness of evaluations of M twiddle depends on the correctness of inc twiddle, but then the correctness of inc twiddle, the way we're checking it, depends on correctness of M twiddle. It turns out that you can break the circularity. Maybe I won't try to indicate how. It does all work out in the end. So maybe I'm flagging like you could be worried that M twiddle is coming up here. It turns out not to be an issue. Basically, the very first time the prover deviates, if it's cheating, this sum check would manage to catch that deviation no matter what. So the circularity it turns out not to actually be a circularity. Okay, so this is the constraint system. So what this is saying is, look, if cell K is not is just not written at time j, its increment should be 0, right? So WA of kj spits out 0 if k is not the cell written at cycle j. So this term ensures that anything that's not touched at cycle j is the increment better be 0. And then if cell j is written cell k is written at cycle j, this spits out 1. And then wv twiddle of j is the actual value written at that cycle. And this is supposed to be the value, stored, just before that write at that cell, at the cell that's being written. And so, I'm trying to think whether this LTE here should be strict. This is less than or equal. Maybe it should be just strictly less than. To not include the rest. Anyway, so I have to think about that a little more. I think the paper has strictly less than, but also had, the read at a given cycle before the write, and now I switched it to the write before the read. Anyway, so the point is this term does an evaluation of M to get the value, stored at the cell being written just before the write. And so, whereas WV twiddle of J is the value of the write. And so this is exactly the increment, the correct increment for the cell that is being written. And so you have a constraint system. So this is memory size times num cycles constraints. But shout was the same way, that it was, had a really, really, large number of constraints. We're not happy with the prover spending linear time and the number of constraints here. But it turns out that the constraint system is super sparse because WA twiddle is so sparse. There are k times t. This is a size k times t polynomial, but only t non-zeros. And not only are there only t non-zeros, for every j, for every cycle j, there's exactly one non-zero. So that's like a ton of structure in the WA twiddle, polynomial to exploit to try to make the prover fast. So you just apply Spartan to this constraint system. People also call this the zero check PIOP. So that is the verifier picks like an R and R prime at random, from field to the log K times field to the log T, and confirms that the sum over all kj in 0, 1 to the log k by log 0, 1 to the log t of eq twiddle of r comma k times eq twiddle of r comma j times the right hand side of the constraint. I guess the constraint would actually be like inc twiddle. Maybe I'm calling it R inc twiddle now. I don't know. No, inc twiddle of kj, minus the right hand side of the constraints, WA twiddle of kj times, WV twiddle of j minus M twiddle of kj. So, it's a mouthful, but, that's it. You apply one sum check. This is basically confirming that, something resembling a random linear combination of all the constraints is 0. So what I wrote here is in these parentheses, which I'll now circle in red, this thing is 0 for k comma j if and only if this constraint is satisfied. I just subtracted the left hand side from both sides to get 0 equals blah, and I wrote that blah here. So this is like taking a random linear combination of a bunch of values that, should all be 0 if the prover's honest. So that sort of, up to some small soundness error, this whole thing is 0 if and only if all the constraints are satisfied. Okay, and now, as I've said, we have a sum over k times t terms where k is memory size. But, because inc twiddle is sparse and WA twiddle is sparse, only t of the terms are non-zero. even before this subtraction, so only T, evaluations of inc are non-zero, and only T evaluations of, what's subtracted from inc, WA K comma J times, WV twiddle minus M twiddle are non-zero. And so, you open up the sum check proving procedure, and you see that, the prover winds up only doing field ops if you're a little clever about things, that kind of grow with T, really K plus T, field ops for the prover. And I'll just wave my hands there. But you can get that completely generically. And then the rechecking sum check is the same kind of thing. Maybe I will write it out just because it is important. Like, ultimately, the prover's original claim was, hey, I can give you query access to RV twiddle, and that's what the rechecking sum check is for. So I would feel like I left out a major part of Twist if I didn't tell you what that sum check is. So let me just do it. So RV twiddle, the actual read values corresponding to the actual, writes at a random point is just let's see. Here it is. So you sum over all K and J in 0, 1 to the log K, memory size, by 0, 1 to the log number cycles. You have EQ twiddle of, let me call this R prime, of R prime comma J times RA twiddle of K comma J times M twiddle of K comma J. Okay, and so what's going on here is, remember, M twiddle stores the actual, M twiddle of KJ spits out the actual value stored in cell K at time J. And RA, twiddle tells you which cell was read at time J. And so, you're summing over a whole bunch of, K here. RA twiddle will just kill any K that's not the right K. That's not the K that's read at time J. And for the right K, it spits out 1, and then, multiplies that by the actual value, that the read should return, which is the value stored at cell K at time J. And then this EQ twiddle here is there because, think of this as like the cycle we care about, even though it actually lives in the whole field rather than the Boolean hypercube. So we have a sum over J here, and we want to kill all J that's not the actual J that we care about. So EQ twiddle does it. So EQ twiddle, kills all J being summed over that don't equal R twiddle, R prime, if R prime were in the hypercube. Right. And so you put all of this together, and you look at the right hand side and you say, oh, this is multilinear in R prime, and also if R prime is in the hypercube, it spits out exactly the right read value. Oh, the right hand side must actually equal RV twiddle at, of R prime, because it's the right hand side is a multilinear polynomial that spits out the same thing as RV twiddle whenever R prime is in the hypercube. So that's the read set checking sum check. To summarize the whole protocol, the prover commits to inc twiddle. Okay. We apply the rechecking sum. Let's see. So we apply the rechecking sum check. Okay. At the end of the rechecking sum check, the verifier has to evaluate RA twiddle of some random point. Let me just say random. It has to evaluate EQ twiddle at some random point, but that can do that on its own in logarithmic time. It also has to evaluate M twiddle at some random point. Okay, and so this the verifier gets from the commitment to RA twiddle. because our RA twiddle was committed, before the protocol even began. Same with WA twiddle and WV twiddle. M twiddle we're gonna deal with later in the protocol. So just put a pin in that. Then we apply the right checking sum check. Okay, at the end of the right checking sum check, just let me remind you what that is. The verifier needs an evaluation of both of these equality polynomials, but it can do that on its own logarithmic time. It needs an evaluation of inc twiddle, WA twiddle, WV twiddle, and M twiddle. So let me try to remember those. So it was inc twiddle, WV twiddle, WA twiddle, and M twiddle. Yeah, and these three evaluations come from the commitments because each of these things is committed by the prover. So we need V needs evaluations, one evaluation each of these things. So these evaluations for inc, WV, and WA, come from the commitments to them. And now M twiddle wasn't committed, so we need M twiddle of random here as well. So what we're left with, the only things we haven't dealt with are the two evaluations of M twiddle, and there we invoke, I call it the M twiddle evaluation sum check. In the twist and shout paper, M is val, so it's called val evaluation sum check. But that applies. M twiddle of random, R. Maybe I'll call it R comma R prime now. Remember that was just the sum over cycles J of what was it, inc. RJ times LTE R prime comma J. So that, so you apply sum check to this thing. At the end of that, the verifier needs an evaluation of inc and an evaluation of LTE. It can get LTE evaluation on its own in logarithmic time, and inc, it gets that evaluation from the commitment to inc. So that's it. That's all of twist. Yeah, and so I guess the summary, maybe I should say something a little bit about the benefits of twist over prior work. So I will say one or two things about that, but let me just pause here. This is twist. This was a complete description of twist. So it's three sum checks, right checking, rechecking, and then this M twiddle evaluation thing to get any needed evaluations of M twiddle. That's it. Does anyone have any questions about twist and that summary?
I actually have quite the same question I asked about one hot ink, about ink being one hot. I was trying to understand how write how writing check how writing sum check helps here, but it's still but now it feels like in that constraint system that was described, a bad prover can actually bring uh, another value increment in the single right. I mean, just put another value to another register. And while we are looking at it, could you also put the previous line into view?
Here?
Yeah, yes. I mean, it's demonstrational.
Yeah, so sorry, the question is like how is the verifier getting a guarantee that ink twiddle is one hot?
Yeah, because this real ink or ink looks like nothing stops.
So this
Nothing
is what I would say. So WA twiddle is separately checked for one hotness. Okay, and then ink inherits one hotness from WA twiddle's one hotness. Okay, so I didn't mention that today, but we talked about it in detail last week for Shout. is, the addresses, of all the reads and writes are supposed to be committed in one hot form. But the prover could cheat. And so we give a very efficient way for the verifier to check, with a separate application to SumCheck, that all the addresses are indeed one hot. I'm actually curious to think about carefully if you really need that check. I haven't had time to think about it, but maybe, not having one hot addresses doesn't really, let the prover cheat somehow. I don't know. It would be nice if that were the case, because at least in Shout, checking one hotness of all the committed addresses is a significant fraction of prover time. But anyway, so WA twiddle is one hot, which tells you that, the right-hand side of this equality here is also, one hot, because if WA twiddle is 0, then the whole right-hand side is 0. And so, and inc here is being, its evaluations are being set to whatever's on the right-hand side. So that's how inc is getting its one hotness, is we know WA twiddle is one hot. It's been checked separately, and so that makes inc one hot as well, due to the constraints that are getting checked in the right checking SumCheck. Does that clear things up at all?
Yeah, that makes all the sense. And great question about if we'll see somebody could get rid of it.
Yeah, that'd be really cool, I think. But also might be impossible. I don't know. Yeah. Cool. Any other questions?
So, do we need that right SumCheck to be equal to 0 or greater? I didn't get that
Yeah,
part.
sorry. Yeah. So like checking, it's checking constraints. So, what this sum here, the sum on the right-hand side here, what this is doing, you should think of this as summing up all of the constraints, so like inc twiddle of KJ minus, whatever the right-hand side of this equality is. If the constraint is satisfied, then inc twiddle minus the right-hand side is 0. So we want to make sure all the constraints are satisfied. That's equivalent to saying all the increments are correct. And so we want to make sure that, every single, term of the sum is 0. And so we're taking these things that should all be 0. We're multiplying each of them by like a random looking value and summing them all up. So that's like conceptually like a random linear combination roughly of all of these values that should be 0. And so, if they all are 0, the sum is definitely 0. And it turns out if even one of them is not 0, then with overwhelming probability over these random values here being fed into the EQ twiddle things, the sum will not be 0. So applying the right checking SumCheck, which just computes this big sum, is kind of just confirming that every single one of the constraints is satisfied.
And we do the random linear combination because if we just did the subtraction, we could get 0 by like summing stuff, right?
Yeah, things could cancel out. So you could have
Okay.
1 and -1 and 2 and -2 and whatever, and then you add them all up and they spit out 0. But in fact, all of the constraints are not satisfied. So if you take a random linear combination, then, it's kind of like as soon as there's one non-zero thing, when you multiply it by a random thing, well, now you're just, completely random field elements, and the probability of getting perfect cancellation is teeny tiny.
Okay, but that sum must be 0, right?
Yeah. So the right checking SumCheck says, look at this, compute this big sum, make sure it's 0.
Okay, I'm just confused because of the greater sign in the left. That's why I was asking.
Oh, sorry. That's
Okay.
question mark.
Oh, okay. Never mind.
Sorry about that. Sorry for the horrible handwriting. Apologies. Yeah. Good. Any other questions? Okay, so let's briefly talk about performance and how it compares, and then that's it for today. So I guess as with lookup arguments before, like before twist and shout, the old way to do read write memory. Well, I guess there were two ways. So one was like just Merkle hashing. So this means like every time you do a read or write to memory, the prover is going to be, kind of conceptually maintaining a Merkle root of all of the contents of memory. And every time there's a read or write to memory, you have to update the Merkle root and prove you updated the Merkle root correctly. And that's just like really, really terrible. There's kind of no other way to put it. That means every read or write to memory, you're proving, logarithmically many hash evaluations. That's just many orders of magnitude worse than what we discussed today. So the other thing, the other way to do things is, boils down to permutation checking. So kind of, we would somehow derive, a big vector from all of the committed, read addresses and write values. We would derive two big vectors and somehow arrange for the two big vectors to be permutations of each other, if and only if, all of the read values are the correct ones. Actually, as far as there's kind of two variations of how you do that reduction to permutation checking. And people don't seem to attribute the approach to the right works, as far as I can tell. So, the old work, like pre-Snarks, that all of this is based on, is some work of Lipton. People do get that attribution right, and Blum and others, Blum et al. This is from the late 80s, early 90s. Most people get these attributions right, but as far as applying those techniques in modern Snark design. As far as I know, the earliest papers to do it are VRAM, which is involves kind of the way you go from memory checking to permutation checking. This involves some kind of resorting, by memory order. Kind of you take all the reads and writes ordered by time and regroup them by which memory cell they access. And that's where permutation checking comes in, to make sure that, the reordering from time into memory order is actually a reordering. That's just the permutation check. And SPICE. And so, this is a 2018 paper. VRAM's about the same time. So people keep attributing, so SPICE avoids resorting. People seem to attribute these techniques to later works. I don't know why, if people just don't know about VRAM or SPICE or what. Anyway, and so because they involve permutation checking, there's a grand product being computed of size. Typically, it's like memory size, plus the number of memory operations. And so that's really what twist and shout avoid. So twist is three sum checks, and okay, well let's see, how do I want to say this? So there are kind of two components to what the prover does in twist and shout. There's what it commits to, and then the sum checks that it does to prove that the committed data is correct. So what the twist prover commits to is the write addresses, the read addresses, the write values, and that's it. And use and inc. Okay, and you can't avoid, as far as I can tell, committing to these things. It's nice you can actually avoid committing to the read values, because that's a virtual polynomial. You can't avoid committing, as far as I can tell, to these three things, because you don't, these just specify the problem, the reads and writes to memory. So you just simply don't have a problem specification without these, right? Like, you don't know what are the reads and writes to memory you're looking to check. Well, unless you committed to write addresses, write values, and read addresses, you don't even know, right? So this is the only extra stuff being committed, and this is just one field element per write per cycle, and it's a small field element. So this is almost exactly optimal. I'd say twist may well be literally optimal on the commitment cost, because it literally only commits to the addresses and that's it. Here we have kind of what feels like the optimal thing, but plus the increments. But the increments are not like a major cost, because it's only one value per cycle, and it's a small value. And then once these are committed, we apply three sum checks. So the comparison to the grand products is, we discussed it last time, but you sort of have 3 choices for grand products. So these are like the, the pre-twist options. So the grand product choices are, what one would be GKR applied to a binary tree of multiplication gates. This is the fastest for the prover, but it has log squared, T proof size. Whereas, so it's like logarithmically many sum checks instead of 3. Then there's Spartan applied to like a binary tree of multiplication gates. This has log T rather than log squared T proof size, but it's an order of magnitude slower because the prover has to commit to a bunch of random values in Spartan, unlike in GKR. And random in the grand product setting, and committing to random values is super slow. And then your third option would be some univariate, options, like univariate sum check or something, and that's even slower for the prover. And so what Twist, should achieve, based on very careful counting of everything the Twist prover does versus like the previous known provers, is even if you compare to GKR where the proofs are much bigger, I think the Twist prover commits. So Twist. So if you look at like Spice, which I do think is the fastest prior memory checking argument, not only because it avoids resorting, I think it's just faster even if you ignore the cost of sorting. So Twist commits to something like 2x less data than Spice. And on top of that, it does like something like 2x or about 2x less field work than Spice. And that's Spice with the GKR grand products. And so, it also has, shorter proofs, because I'm comparing right now in this sentence here, Twist to Spice with the fastest grand product argument, which has much bigger proofs than Twist. So yeah, like asymptotically, it's sort of like, if you equate the same proof size, I think Twist is an asymptotic improvement. For the prover, if you don't equate proof size, if you compare Twist with log proofs to prior work with log squared proofs, probably Twist, is asymptotically matching the previous prover time, but concretely it's going to be 2 to 3x faster because it's improving. It sort of doesn't matter what fraction of the prover's work is committing versus sum checking. I actually think it's almost all sum checking now because we brought the commitment cost down so low that sum check dominates at this point. But we get a 2x to 3x speed up for the prover in both parts of the protocol. So kind of no matter which fraction of the protocol is due to which part committing versus sum checking, we're going to get a 2x prover speed up. Could actually go up to 3x or something with Twist. Okay, so that is Twist. Hope it was interesting. And yeah, maybe next time I'll figure out what we'll discuss. If anyone wants me to kind of provide some commentary on ZKVMs in general, I'd be open to that as well. But we still have Fry to cover. We still have Growth 16 and its predecessors. We still have Recursion and Nova. Okay, so let me know if you have any questions. Otherwise, thanks so much for hearing me talk about Twist. Any questions?